Hello everybody, back again to talk about osmosis. This is wrapping up the section on physical properties of solutions. We'll move on to chemical kinetics after this, which is a real interesting chapter. We're going to finish up with osmosis. This is on page 17-ish to 18 of your note set. It finishes up these notes here after we do the freezing and boiling point section. We go on to osmosis. So I'm going to use my note sets for this lecture. So osmotic pressure is often osmosis and osmotic pressure related terms. Osmosis is the process. Osmotic pressure is what you measure. Osmosis is the flow of water or other solvents, but we'll focus on water because that's really where you're going to, in your science that you study, most of you, the emphasis will be on water. So it's the motion of the flow of solvent, often water, from a solution to from one solution to a solution of higher solute concentration. So the idea is this. Let me draw a system that's like a U-tube. And it has a membrane here. This could be a model for a biological cell. The membrane is semi-permeable. We design the membrane, or nature designs the membrane such that water can go through the membrane, but other certain solute particles, either salts and or sugars, it depends, sometimes it's large structures like proteins, but it will impede solute particles. It's either one or different types, depending on the type of membrane. So this is called typically a semi-permeable membrane. It's permeable to water with no or limited permeability to solutes, or at least a limited class of solutes. So, for example, let's just put on this side of it pure water. Put a little wavy action here. It's just water by itself. And on this side of it, you've got water that's got salt in it. Let's just say it's got salt particles, NaCl, floating around here. So let's say it's NaCl aqueous, and we've procured or manufactured a membrane that allows the flow of water through, but does not allow the flow of salt through the membrane. So you can have, you're going to find, I drew it the wrong direction actually, is you're going to have motion of the water from the direction where you have a higher concentration of water over here to the saltier side. Water is going to be flowing this way preferentially, as long as you have the membrane constructed such that it has permeability to water and doesn't have permeability to salt. If it does, then you would get an even distribution of salt and water on both sides. So what happens is this side builds on up. You're going to get an increase in its volume relative to this. It's going to decrease down here. Osmotic pressure is the pressure that you have to apply to the system. Let's say we manufacture this in such a way that we can apply pressure to stop or impede the flow of water across that membrane. The equation of state that describes that is the osmotic pressure. There's molarity, R, and T. And if we're in general, I'll write it in the general form. You have the Van 't Hoff factor. This capital pi is osmotic pressure. Again, that's the pressure to impede the movement of water across that semi-permeable membrane from pure water or a low solute content water to a side that has that's a solution or has just simply a higher concentration of solute than the other side. That to me, they do clump this with colligative properties. I have no problem with that. I would consider this more of a diffusion-related process. Somebody could argue that it still depends on particle type, particle concentrations, not particle numbers, not particle types. I would kind of argue against that, because if you have a particle that diffuses against the membrane, can diffuse through the membrane, then you will not see this effect. So, it's an arguable point, but what is not arguable is this is very important in biology, all forms of biology. You can have, for example, if you have a cell sitting there and has all cells have a certain salinity, certain concentration of salts and other solutes in it, and you put it under, for certain membrane types, with an environment around it that's extremely salty, has a high solute concentration, the cell can shrivel up. We call that a hypertonic solution. That's really a biology term, but I'll use it. It's an important term for those of you going on to study biology, because water is passing through the membrane and going into the environment around it. Conversely, so that's hypertonic. Hypotonic's the opposite, where the cell itself is saltier than the exterior, or maybe the exterior could even be pure water itself. So what's going to happen is the high content, the region with the high concentration of water will diffuse through the membrane and cause the cell to swell. We call that being hypotonic. Isotonic's the case where you would ideally want to be. Isotonic is where you have a equal or similar solute concentration within the cell and on the outside of the cell. So all this relates to osmotic pressure. We will not deal with cells per se, but we're going to deal with this equation right here. We'll calculate out the osmotic pressure associated with the process of osmosis with a problem. So instead of molality, we find that this models well with molarity. The choice of R, the gas constant, can always confound people. If you want your result to be, for example, in atmospheres, choose the R with atmospheres. Choose the R that's appropriate for the units of the osmotic pressure, pi, capital Pi, that you're trying to get. So let's work the problem. Let's say we have a system set up where we have on one side, we got a semi-permeable membrane. We've got on one side, let's say we got pure water. And on the other side of this is some kind of container, right? So on the other side of the container, we got an aqueous solution of glucose. So it's sugar and water. Glucose is just C6H12, O6. Similar formula to fructose. This is blood sugar, if you will. So we have 2 grams of glucose that's been dissolved to 100 milliliters. The temperature is 25 degrees Celsius. We always need that. A lot of times on tests, I will say in the header or somewhere, the temperature assumes 25 degrees Celsius or 298 Kelvin. And we will convert that to Kelvin. So you add 273 to it, get 298 Kelvin. So this is whenever you do thermodynamic calculations, almost always when you're using R, R's got kelvins in it, you're going to have Kelvin. Here, quick thing to look at is you recognize this as a sugar. It's good to know for exams, because I use them all the time and they're very biologically relevant, is that sugars are not electrolytes, at least not appreciably. So I is equal to 1 here. The Van Hoff factor is 1. If this was NaCl, I would be equal to 2, right? So I want you to calculate the molarity. For the molarity of glucose, I got 0.111 molar. So we're limited to 3 sig figs. The next numbers is 0. If you want to retain it in your calculator for goodness, that's good habit. So we have a 1 here. I'm not going to write that in. We got 0.111 molar. If I want to get this in atmospheres, I'm not going to use R in liter bar. I'm not going to use R in the Joule system because that gives me pascals. I'm going to use it in good old liter atmospheres. So 0.082057 liter atmosphere K-mole. If you've never had me for a class before, there's no reason to memorize these different values of R. I will give them to you free of charge on the test. You get that, you can take it as a bonus. And then the temperature, so use the right R, because I will give you a couple on the exam because different problems, different R's. And then the temperature, you have to convert that, adding 273 to it to 298 Kelvin. And provided I did my calculations correctly, we just go through units really quick. So moles per liter, that's molarity in the denominator. That cancels this. The Kelvin cancels the Kelvin. We're left with atmospheres. So provided I punched it in right, I got 2.71 atmospheres. And again, if we had another system, let's say we did a similar problem with NaCl, then I would, instead of being 1, which I don't show 1 here, you could have 2. If it was something like sodium sulfate, that would give you I equals 3, right? So you have to adjust that. So don't forget how your common ionic species dissolve. You know, I notice sometimes with students, they take the polyatomic ions and they take the sulfur off and they have the oxygens coming off. So do review those. To know the common ones, we will commonly use sulfate, sulfite, nitrate, nitrite, certainly the hydroxide ion, carbonate ions common, and there's other ones that are more rare. You know, like we're not going to do too much with dichromate and things like that. Once in a while it might come up in a redox problem, but certainly the common ones you should be familiar with. Well, on that note, that's osmotic pressure. So that would apply that to stop the flow of water, we would have to apply 2.71 atmospheres of pressure, which is experimentally doable, to stop the water from moving across that membrane. I'm not going to derive that relationship. We don't really have that kind of time, but it is readily derivable, the equation I'm using this calculation with. So like derivations, you can take me for physical chemistry in the future. You'll have all the derivations you want. So this was osmotic pressure. I will begin making videos for awesome kinetics, chemical kinetics, which is a challenging chapter. I looked at the properties, the physical properties of solutions, the warm-up chapter, learn some practical calculations, get ourselves in the grooves of putting some numbers on paper. The kinetics is more intellectually challenging. So on that note, I'm out of here. Have a great night or a great day. Take care.